Okay, so we're going to continue what you were working on yesterday with continuous functions, or continuing continuity. Ms. Fowler talked to you yesterday about some different kinds of functions that we can always assume are continuous everywhere. Anybody remember them?
Polynomial.
And one polynomial was one of them?
Root,
rational functions are always trigonometric, and then the root functions as well, okay? So today we're going to kind of tack on to that a little bit. Do you know what this fun notation is? Do you remember that?
Oh, no.
This is not a multiplication symbol, it's an open dot. F of G, which is called fog. Yeah, no, but it's called, it's not really an O, it's just a little
G of F.
Right, and G of F of X, okay? This is composition. Yeah, fog and gaw, composition of functions. So this is when you form a new function by plugging one function into the other one. So you have a new function that's composed of two separate functions. And so f of g of x is one way to write it, or if you use function notation, that looks the same as that, okay? So this exciting theorem just says the same thing about as it did about the polynomials and rational functions and so forth. If you have two functions that are continuous, and you combine them to make a, a composition of the two of them, then that new function will be continuous as well. Okay? So this allows us to get crazy with our functions. You good at that? No? Okay, so let's take a look at some composition of functions thingies. So we'll start out with an easy one. Where is the following continuous? And we're going to look at the sine of x squared. And we have the x squared in the parentheses to emphasize this whole composition of functions. So this is two different functions put together. The sine function is obviously a, I'll say it all at the same time, trig function, and the x squared is a polynomial function. And so you could rewrite h of x as f of g of x, where f of x is what? Sine of x. And g of x is what? X squared. Okay. Where is x squared continuous? Everywhere on its domain. Where is sine of x continuous? Everywhere on its domain. So this little theorem that we just went through tells us that the sine of x squared is also continuous everywhere on its domain. Okay. And what is the domain of these two things? What's the domain of x squared? How far does it go that way, and how far does it go that way? Negative infinity. How about sine of x? Negative infinity. So this is everywhere on its domain, which you can write as all real numbers, or you can say negative infinity to infinity. Okay? All right, let's do a little more complicated one. Let's look at capital F of x, which is okay, so if we look at this one, how many functions do we have to put together to make this? You have this guy right here, which is a polynomial, right? You've got this guy right here, which is a root. And then we can combine those things there to make another polynomial, and then the whole thing is a rational function. So there's quite a few different things going on here. So they want us to say, in this case, f of x, the big overall function, is 1 over x. Okay? And then g of x is, what can I substitute into 1 over x to get closer to this right here? X minus 4, very nice. Very nice. And then where do they go? H. H of x is, what can I substitute into x minus 4 to get closer to this? I need this x to be a square root, so that would be the square root of x. And then k of x is equal to x squared plus 7. So that's a lot. But I take the x squared plus 7 and put it into the square root, change that to the square root of x squared plus 7. Then take that and put it into here, and that changes into the square root of x squared plus 7 minus 4. And then put that into here, and that changes it into 1 over the square root of the x squared plus 7 minus 4.
Basically, just make the problems way harder.
Yeah, pretty much. Well, for absolutely no reason at all. So, are all of those continuous on their domain? On their domain, yes. Okay, so that doesn't necessarily mean that they're continuous everywhere, because the domains of these things are not necessarily all real numbers. What are some things? What would we have to worry about here? Okay, well, you got the square root, so you can't have a negative underneath the square root, but is that possible in this thing, since it's x squared plus 7? No. So I have to worry about this thing right here. I can't divide by 0, right? So this thing right here can't equal 4. So we could do some math and figure that out. You could say, okay, so the square root of x squared plus 7 can't equal 4. How do I solve that? Square both sides. So x squared plus 7 can't equal 16. How do I solve that? Subtract 7. So x squared can't equal 9, which means x can't equal 3 or negative 3. Okay, so you can use that to figure out your domain. All right? Okay, and then there's one last thing in this section, which just so happens to be the last section in the chapter. So get excited about that. This falls under the thing that Nate just said, or was it Nate or Shad, about we took an easy problem and made Tyson and Shad really complicated. Okay, we're going to take a very easy concept and write it in a super fancy way, so you can feel really smart. Okay, so suppose.
Got some English though. Really? Wow. Nice. Oh, it is useless. I like it.
Okay, suppose that f is continuous on some closed interval a to b. Would anyone like to come up to the board and draw a continuous function on the closed interval from a to b? Because we're trying to imagine some function that looks like. Anybody want to? You know what? What? You might do it wrong. Nobody?
Just go up there and draw one.
Okay, so yeah, what's the main idea? Just go up there and do what? You just have to draw like some sort of squiggly line, right? Okay, and that's a continuous function. What is this over here? That's A, and what's this over here? B. Okay. So you're just going to pick a number, yeah, that's all right.
Negative.
Negative, it is a negative, but you know, it doesn't have to be. So we have just some random function f that's continuous over the closed interval a to b. So I guess. Okay.
You're back.
All right. Then it says.
American job.
Okay, then it says let n be any number between f of a and f of b. So when we say f of a and f of b, now what are we talking about? The A and the B were the x values. F of A and F of B are the y values, okay? Because that's the answers that you get when you plug in the thingy. So let's make this a little bit more interesting. At least just a little bit. Okay? All right, so here is F of A, right? Yes, that has some value. Thank you, Casey. There's F of B, and so I'm getting F of B if I went over here, straight up to the function, and then straight across. That's straight across. Perfectly straight. Okay, so that y value right there would be F of B. Okay, so we're going to let n be any number in between F of A and F of B. So it could be anywhere, any y value in there. So you with me? Okay. The only way that this won't work, I shouldn't have put a period there, is F of A can't equal F of B. They can't be the same number because then you couldn't pick a number in between them, right? If F of A and F of B were the same thing, then n would not exist, okay? All right, here's what the intermediate values theorem tells us. Then there is some number C in the interval from A to B such that if I plug C into the function, I'll get n as an answer. So somewhere along this interval, if you pick any place here, any random number n, okay? So if you look at n and let's say right there, if I plug in C, I'll get n as an answer, okay? And that's just a simple, pretty straightforward consequence of the fact that this function is continuous, because how's the only way that that would not be true? If I pick this as my n, what would my graph have to look like if there was no value C anywhere so that the function took on that value when you plugged it in? What would have to be in these places here? Yeah, discontinuities of some kind, and so it might be little holes here, okay? Then that would mean that that couldn't work, or you could do some sort of whoops, let's go green. Some sort of infinite discontinuity or something right there, and so somehow those pieces would be missing. All right, so it's pretty straightforward. It's not like rocket science or anything. If this is a continuous function, if you pick two y values, pick one in between, somewhere along the line the graph is going to cross that y value. Okay? All right, so who cares? Let's do a problem that uses this. Okay, so let's take this fancy equation, 4x cubed minus 6x squared plus 3x minus 2 equals 0. And we're going to use the intermediate value theorem to show that there is a root somewhere in between 1 and 2. Nice. What is roots of an equation, what is it or what does it look like? Where do the roots of an equation occur on the graph? When y equals 0, right? So anytime it crosses the x-axis, when y equals 0, those are the roots of the equation, okay? So what this question is saying is we need to show that this graph crosses the x-axis somewhere between 1 and 2, right? And it's really very simple. If if I take and plug 1 into there, what do you get? The -1? Okay. If I plug 2 into there, what do you get? A little trickier. We got some calculators out now. You got 12? Okay, so what that means is if we think about the graph, and we don't know exactly what the graph looks like, but what do we know is true about the graph? What have we just been talking about for the last 2 days? We know that there's a root, yeah, but what is the title of this? It's continuous, thank you. We know it's a continuous graph. Why?
Polynomial.
Polynomial, okay. And so what we have done is we took x equals 1 and plugged that in, we got -1, yes. And we took x equals 2, this is 1, and this is 2. We plugged in 2 and we got 12 as an answer, okay. So since this is a polynomial function, which means it's continuous, what has to happen between this point here and this point here? It has to cross the x-axis. So in this case, the value for n that we wanted to choose would be n equals 0. So since f of 1 is negative and f of 2 is positive, there's no way I can draw a continuous function that connects those 2 points without somehow crossing the x-axis, which means that it must have a root in between 1 and 2. Okay? Do we know what that root is? No. Do we care? No, because that's not what it asks us to do. So this came out negative, that's positive. It's got a root in between somewhere by the intermediate value there. Okay? Yeah, we'll try her trick from yesterday. And that's all I have for you today.
Ah.
Oh yeah, I was a little fly. Forced.
That's not
Oh yeah.
Oh, you're sick. Still in morning.
Or what?
Do we have?
I think classes are back in the gym. Still in morning for JR.